let's travel back to the beginning of Earth history, to the Hadean Eon. So recall that Earth formed about 4.54 billion years ago, and that marks the start of the Hadean Eon. And it ran for about 500 million years up until 4GA. So here, capital G is a metric prefix, giga. It means 10 to the power of 9. Now that is a 1 followed by 9 zeros. Annum means years ago. So here we're looking at billion years ago. And at the beginning, Earth was very, very hot. So hot that it was molten. It did not have a solid surface. And then about 4.4 billion years ago, Earth cooled to the point where it was able to form this ultramorphic rind on the outside. So once again, there was no solid rock. It was just this rindy material, this crust on the outside. And if you're not sure what an ultramorphic rock is, let's think about an example of a mafic rock that you might be familiar with. And that mafic rock is basalt. Basalt is an extrusive igneous rock, and it forms much of our sea floor, as you'll see even more of in the upcoming tectonics videos. And a mafic rock is really low in silica content. To give an example of an igneous rock that is higher in silica content and therefore less dense is granite. Granite is an intrusive igneous rock and forms much of Earth's continental crust. So looking here at this ultramorphic rind, that means it's extremely low in silica content. And also keep in mind that at this time, the moon had just recently formed. It formed 4.52 billion years ago. And the moon did not look how it looked today. The moon was still very hot. It was also geologically active, and it was so much closer. It would have been the distance from the northeast US to Australia. That's how close it was to us. And so it would have been this giant, really fiery moon in the sky. And then the surface of Earth was not at all solid. It was molten, no rock present, certainly no plate tectonics yet. And it was getting bombarded by meteorites. So it was a very dangerous place to be. And it had a really thin, wispy atmosphere made of hydrogen and helium, which the planet did not have a large enough gravitational attraction to hold on to such small atoms. So they drifted off or diffused off into space. So Earth's first atmosphere was very thin. It was molecular hydrogen and helium. Moving on forward in time to the Archean. Or just kidding. First, let's talk a little bit about differentiation. So as Earth continued to cool, what happened is it separated out based on density. So the more dense iron materials sunk down into the center of the Earth to form the core. The less dense materials, those rocks that were cooling on the surface, rose up and formed the continental and oceanic crust. And then in the middle, we have the mantle, which is somewhere in between iron and igneous rock as far as density goes. Although, yes, we do get much of our igneous rocks from the mantle. It's just the rocks in the mantle have a much lower silica content, or the composition of the mantle is much lower in silica content, which makes it more dense. So we have the less dense materials up near the top of the Earth and the more dense down at the core. That is differentiation. And so as this happened, we had the very beginning of the rock record in the Archean Eon. So finally, we're getting some rocks that aren't just like melting away instantly. And so also at this time, the Archean Eon spans from 4 to 2.5 billion years ago, we also had global oceans, vast global oceans. So that's at about 3.85 billion years ago, we started to get these oceans. And then at somewhere between 3.8 and 3.2 billion years ago, we had the first life on Earth begin to emerge. And also at this time, we had lots and lots of volcanic outgassing. And so we started to get an accumulation in our atmosphere. So this is the formation of our second distinct atmosphere, where we have water vapor and carbon dioxide and ammonia accumulating from volcanic outgassing. So now let's bring this back around to the faint young sun paradox. So at this point, when we have liquid oceans and life forming, there are a few different reasons why, or hypotheses at least, why Earth was warm enough to have liquid oceans even though the sun was so faint. One looks at the composition of Earth's atmosphere from volcanic outgassing. If Earth was very much tectonically active and there was lots of volcanic outgassing happening, then we'd have a very thick greenhouse gas atmosphere, which would keep the planet warmer. And as Carl Sagan pointed out, we could have also had more methane in the atmosphere at that time. Now, methane is a very short-lived greenhouse gas in our atmosphere as we look at it today. It lasts maybe a decade or so, but it's much stronger, has much stronger greenhouse effect than carbon dioxide. But the reason it only lasts in our atmosphere about a decade or so is because it reacts with oxygen. While looking at the second distinctive atmosphere in Earth's history, there wasn't oxygen. So methane could have been around for longer than a decade, easily. So the composition of the atmosphere is one reason that we probably had liquid oceans. Another is that Earth did not form that long ago at this point in time. So it was still likely very toasty warm. So if you look at Earth's energy budget, we get about 99.97% of the incoming energy today from the sun. But we also get some incoming energy from Earth's interior, from Earth's radiogenic heat, which is left over from its formation, and also from radioactive decay processes. Or we have the primordial heat, Primordial heat is left over from Earth's formation. Radiogenic heat is from radioactive decay processes. So at this time, we would have still had lots of remnant heat from Earth's formation. Plate tectonics would have been moving around much, much faster at this time because everything was still so warm and active. And